All right, good morning, everyone. Happy to have you all today as well. Going to be another exciting day, and we have another exciting session as well. So I'm Sucheta Correa, postdoc at Stanford here. All right, so we have a session on galaxies and foundation models by David Hui, Marc Huertas-Company, and Francois Lanous. I'll just take you away. Yeah.
All right. So thank you very much. I would like first to thank the organizer, Dalia and Risa and Joe, everyone for having me here. That's great, having us here. And proposing us this challenge of coordinating a talk and with, interesting instructions. So it forced us to talk a lot and then trying to figure out something that has a workflow. So yeah, first I'm gonna, so a few words about us. So please, I'm Marc. I'm gonna talk about, so I work at the ISC in Spain, a little island in the middle of the Canary in the ocean. And I'm gonna talk about, the field of galaxy evolution, which is very challenging, and how AI can help and pose some questions. And then,
And I'm François Lanous. I'm a research scientist at CEA Paris-Saclay in France. My background is in observational cosmology and Earth surveys, but also applying AI to these data sets. And I will cover the recent shifts in methodologies that we have started to observe towards foundation models.
And I'm David Foey. I'm sort of one of the other people who stick out like a sore thumb. I'm a computer vision person originally. I got my PhD in robotics, but for the past 5 years, I've gotten really interested in applying computer vision to problems in the basic sciences, especially in astrophysics. So I've primarily worked in solar physics, but it's a lot of fun to be here and to learn about all sorts of interesting projects and sort of parallels. So I'll be talking about foundation models. I'll be trying to sort of perhaps throw a wet blanket on some of the ideas, which is my role, I think.
all right. So we're gonna do the talk in a row and then get questions at the end. Okay. Good. So current state of the field, which is a very open question. So I'm going to talk about physics, astrophysics, and I'm going to talk about, try to make a bridge between what astrophysics, how AI has been helping, what's the state of the field, and how, pose some problems so that, we can introduce the methodologies. Okay, so galaxies. So when, what's a galaxy? I ask people around here, not everyone is an astronomer here. Yeah, sorry, I would like to walk around. So I'm going to take that. And does it work? Yeah, okay. So if you think about a galaxy, you probably will think something like that. We've seen all these beautiful images with spiral arms, and which is kind of similar for our Milky Way that you get here. Of course, this is not a real picture, but this is the image we have as an outsider of a galaxy now. Now, if you are more like into astronomy, you would start thinking that galaxies will depend whether you look how you look at them. It's telling a different story about what are the components of these galaxies. So if you look in the optical, you're basically seeing stars like our sun. If you go towards the radio, you see cold gas, so the fuel for star formation. And if you go towards the X-rays, you start seeing hot gas heated, for example. So it tells you a different story depending on what wavelength you're looking at. And if you're even more an astrophysicist, you're going to say that this is more like what a galaxy looks like, right? It's something that it's a tiny fraction of luminous light that we have embedded in some kind of dark matter halo, right? And so if you start zooming out, this is more or less the picture we have. We've been hearing yesterday about cosmology. So if you look at the universe at very large scales, it's basically a tissue web of dark matter. And as you zoom in into the dark matter, you get into regions that are more dense, what we call halos. And in the center of these halos, you get this galaxy there, okay? So just to give you a scale, so a typical galaxy is 100,000 light years, okay? Just the luminous part that we see. So what's galaxy formation? Galaxy formation is about telling a story of what's the story of baryons in the universe, how they have evolved over time. And we know that these overdensities of dark matter are the places where what we call gas, which is essentially hydrogen, helium to some extent, So the primordial gas that was out there, elements that were there after the Big Bang, get transformed into stars that in turn, produce metals, what we call metals, that everything that is heavier than hydrogen. And so doing galaxy formation is trying to understand how this process happens over cosmic time, how the gas is transformed into stars. And we know now that this is what happens inside these halos. It's a very complicated multi-scale and nonlinear physics, right? Now we are really digging into the center of this where baryons dominates. And so here you have hydrodynamic physics, you have magnetic fields, you have radiation, everything we know. And everything couples this here in a complicated way. So when we try to understand the history of baryons, it's telling the story of how these things couple all this physical system, of course, across cosmic time. So how do we tackle this complicated problem? So there's many ways of doing it, and many people are trying to understand each of these little elements here as, can be studied for a lifetime, right? And we don't understand any of them. But one way, so I'm going to talk here because we're at the Rubin conference, and so in big data conference, one path that we have been following over the past years is by gathering data, so doing statistics, right? And so this is what we call surveys, and basically what we do is we take a random patch of the sky, we observe it, and we get many, many galaxies in there randomly, because we assume that all galaxies are the same. And this is the typical data modalities we get. We get images like that. Every little dot here is a galaxy at a different time or distance. And we also get, if we are lucky, some spectroscopy, which tells you the light as a function of wavelength that we've seen already yesterday. And so what do we do with this data? We need to do statistics. And because basically we are trying to discover what's there. We don't know exactly. So we're going to take this data and do some summary statistics, right? Extract some physically driven summary statistics of this data that we have been putting together over the years. And again, so we get, for each little dot in the image, we're going to get its stellar mass, its star formation rate, so all kinds of physical parameters that we extract from this data. And again, all of these parameters is probably dedicated PhD thesis work of people trying to understand how we extract stellar masses, how we measure star formation rate from this data. So how we go from this is a very physically driven summary statistic and very specialized, right? And so this is and of course you need to get also the what we call redshift or the cosmic time. So one way machine learning has been helping here over the past years is trying to replace these very specific summary statistic extractors that we have been driven pure physically driven physical estimators by some kind of supervised ML. And the main motivation because of that, and I think many of us in this room have played this game with one thing or the other, the main motivation behind that is that because we're getting more and more data, this very specific software is typically not scalable, doesn't scale well to the scale of Rubin. So we said, let's use machine learning there. And we have been playing over the past 10 years trying to replace basically these by neural networks that estimate this summary statistic. I don't have time, of course, to overview this. With Francois, we wrote a review that is now updated, but it gives you already an understanding of what are the typical methods that we use here. Right. And then once we have that, these summary statistics, assuming that we got them, what do we do? And so this field of galaxy evolution is essentially a very exploratory field. We are trying to understand what are the correlation between these summary statistics and to get some physics inside, right? In a very macroscopic way, because you reduce these summary statistics and trying to understand. And one way to do this is by what we call scaling relations, which means essentially we plot one quantity versus the other in this summary statistic plane. Typically, it's a 2D plane with a third dimension, which is time, right? Because we have, the distance tells us something about the time. And this is the things that we like when we see correlations. Typically, power laws. It's typically log-log. And when we see this correlation, this means that there's some physical inside there. If this quantity correlates with this is telling me something about the physics. And then we start working out what could that mean, right? That one is a very famous relation, which is called the main sequence of star formation. And it's telling me that, at a given stellar mass, so one galaxy is big or small, it forms a given amount of stars and always the same. right? It's independent. So dependent of whatever galaxy I look like, if I know its mass, I know how many stars it's forming at first order, right? So this is telling me that the life of galaxies is not completely chaotic. So it's not stochastic. It's some correlation at large scale that has to do that, right? So by looking at these relations, I can get some insights. This is another relation that we like, which is telling us, again, as a function of stellar mass, big, small, what is the chemical composition? Because we have looking at this enrichment of the gas. So you remember gas is transforming atoms into, so hydrogen into metals. So by looking at the chemical composition of the gas, we know, how the star formation has been happening. And again, we see this kind of correlation that, if we know the mass of a galaxy, we know more or less the chemical composition. So it's again telling us something about a large-scale coordination, let's say, or regulation of star formation. And by looking at these scaling relations, we've been trying to put together a kind of framework of how galaxies form. And so because we are seeing that star formation is regulated, it means that you need some constant arrival of gas to maintain the star formation. And this arrival of gas needs to be more or less the same for all galaxies, right? Because, so it should be regulated by some kind of property like the mass. So if you have a halo of a given mass, it will receive a rate of gas that is around in the cosmic web, and this will collapse and will form stars and will enrich the medium at a rate that explains your power laws, right? So it's a simple way of, I'm exploring the data just to have you, so I'm exploring these relations, I'm looking at them, and in an empirical way trying to come up with a physical explanation. It's a very exploratory science in which I'm not going from a model and trying to, so I'm really driven, it's driven by data. Another thing that we like to do, and Riza has played a central role in this, is what is summary statistics, we count galaxies, right? So we do one plot quantity versus the other, or we count. And by counting, we also learn a lot of physics. So it's simple, but it's a very physically informative summary statistics that tells us something. And I'm skipping the details about this, but these plots tells us something about how efficient is star formation. And by looking at these plots, we can know that, in fact, all the gas that goes into the halo is not transforming to stars. In fact, the majority is not. And if you are very massive, you form very little stars. And if you are too small, you don't form enough stars either. And so this, again, drives the thought of, OK, so if all the gas is not transforming to stars, we need to think of a physical mechanism that explains that. So again, you have this data-driven kind of approach, but physically in the sense that the parameters are physics, and we try to come up with some physical explanation, right? And so you think, OK, what could be a physical mechanism that prevents star formation? I need to heat the gas, or I need to expel the gas, because otherwise it will cool and form stars. And so this is what we call feedback, which is a central element in galaxy formation. It means that at some point, you need some mechanism to inject energy into the gas. And again, it's driven by looking at the data, exploring, counting, very simple data exploration. And so what could be the mechanism that heats that? So again, you look at another scaling relation. And you figure out that if you look at the stellar of the mass of stars in the center of a galaxy and the mass of the black hole in the center of the galaxy, they strongly correlate, even if they live at very different physical scales. So this is again telling us that black hole is probably doing something to prevent star formation, because we know it's enough energy to inject energy into the gas at large scales, and we see this correlation again. So again, looking at power laws, exploring summary statistics, we try to come up with a physical explanation for all that. Right? So we have now this quenching mechanism, so this mechanism to heat the gas. And if you push this at the limit, you might be in a situation in that you stop completely star formation. So this mechanism of expelling the gas wins for some reason, or you stop the arrival of gas, and the galaxy stops forming stars at all. There's no more stars forming, right? And this is what we call quenching. And why do we know that this happens? Because we observe them. We see lots of galaxies that are not forming stars. And it turns out that you see them again in scaling relations, right? And if you look at the Hubble sequence, which is how the different shapes of galaxies we observe in the local universe, where we see spirals and elliptical galaxies, it turns out that this relation, morphological relation, by exploring and scaling laws, we identify that in fact it's a quenching story, right? Because these galaxies here that look elliptical, in fact, they are not forming stars. They are the red points here. Okay? So it means, again, it's telling us that this quenching mechanism is doing something. So whatever is quenching galaxies, which could be the black holes, but it needs also to transform the morphology of the galaxy. And again, all these things are just by looking at these simple summary statistics. With statistics, it's important, because if you have only one point here, or you observe random galaxies with a complex selection function, it's very difficult to figure out these relations. So I think one lesson here is that it's very, data-driven, and that you need statistics. Okay? And so by doing this, we have built a kind of global picture of galaxy formation, in which I would say it's a kind of spherical cow model of galaxy formation. But it works well, okay? In which you have things that come in, some gas is transformed into stars, and some other gas is blown up, and at some point you get an equilibrium. And because this galaxy lives in a cosmic web, this is the halo, more or less the amount of gas is regulated by the cosmic web, and it will receive more or less the same amount of gas, depending on cosmic time, of course, right? Statistically, again. So now if you put this kind of spherical cow model, I'm being a bit mean, but in a big computer simulation, very expensive simulation, this is one example of them. You see this flow between dark matter, gas, stars, metals. You start getting things that look like galaxies. So it means that we are understanding at least partially what's going on, right? And this is a big success of simulations. These are an example of observed galaxies with HST, and these are similar mass galaxies simulated by this big simulation. And so you see that they are starting to be indistinguishable. So it means that, and this is a big success over the past decade as well. A few years ago, we couldn't do these galaxies. Right. But I think, the question here, and looking ahead in the future, is how we go from this, working model, I would say, to try to understand the inner parts of this, the physical process going on here. And can we do this with big data or more data? Or it's something else that we need? And I don't have an answer for that, but this is what we're discussing here. So if you look at the details of this, and that's why I'm saying that of this kind of model, I'm a bit late, good. So all the elements of this model, when you're trying to understand the physical insights, we don't understand them. Because either we don't have data, it's too complicated, or with this simple summary statistics, we can describe that. So we know indirectly that there must be gas coming in, but we have never observed it directly, or with very few cases. So this gas that should be diffuse gas that should be sitting around galaxies, we cannot observe it. It's too diffuse, too shallow, we don't have the technology to do that. And we know indirectly, again, that black holes should be doing something, but we don't have a direct evidence for that. It's only, and we don't know exactly how black holes grow. We know that it does something indirectly, and because in some galaxies we can observe these big feedback jets. But this is counted elements. Now, linking how this is affecting the overall galaxy stellar populations is complicated, and one reason is because it's complicated physics, but also it's because they work out at very different timescales. This stochastic accretion of gas into the black hole that typically happens at timescales lower than megayears, and this happens at scales larger than gigayears, right? And I'm accelerating this. So one thing that is important here, and the two elements I've seen that is missing in this picture, are happening at very, very different physical scales, which creates some difficulty in trying to understand all this and simulating that, right? So this is translated in this kind of element here, in which if you get multiple these heavy computer simulations, you get multiple of them with the same initial conditions, they all reproduce good-looking universes, galaxies that look okay, but when you look at the temperature of the gas, for example, they are exact, so they are analog universes. They have very different predictions of what's going on, okay? So it means that, it's not well-defined. So you can get to a good-looking universe, but because it's unconstrained here, you get lots of, it's very uncertain. You can have many ways of heating the gas, many ways of making this happen, and you converge to a same universe. So it prevents some kind of use of these simulations as a predictive power again. Good. And so, in the end, the bottom idea here is that even if we have a good overall understanding what's going on, if I ask some experts here, how do you form this galaxy and how do you form that galaxy, we don't have a clear picture. Okay? We have some ideas, but it's not that we have a complete story about that. We cannot say that galaxy formed that way. And as we get new technology, like with JWST, we get, again, new surprises and more questions than answers, which is also fascinating, but frustrating. So we saw, for example, that, and Brand contributed to that, and our group as well, that when you look at very high redshift or very distant, you observe too many disks that shouldn't be there. Or you observe too many massive galaxies that shouldn't be there. So it, again, poses questions about how all these things form, right? Good. So I'm super late. But so what are we doing next? Okay, so that's the point here. What are we doing? So how do we solve this? How we go from this? How do we get more insights into that with this data deluge? So what we are doing is, as you know, that's why we're discussing here, we're getting more and more data, right? And not only more data, as we saw yesterday, and important by Laurence, an important thing is also data quality, more information in this data. More data and more informative. So we could eventually do the same thing, but scale by a factor of 1,000. So looking at, and now we can do it because we have machine learning. A few years ago, we couldn't. So AI has solved this issue, and François will talk about that. We could do the same thing. So take Rubin data, using, instead of physical models, we're going to use some kind of big foundation model. We can extract these summary statistics, and we're going to do that for sure, and we're doing it already. And we're going to learn things because we will reduce the error bars. We'll probably dominate it by systematics. We're going to look at the scatter of this relation, and we're going to learn more about the physics. But can we do more? And this is what we're trying to discuss here. But because even if we get very accurate scaling relations, we still have in this situation in which we have different models that play with different parameters that are basically unconstrained, and they all converge here to the same physical laws. Okay? So how do you get insight about the physics that is happening here? And so you have problems at the model size that is difficult to simulate, and we have problems because the comparison we do is simple in 2D space or 3D space. So it's difficult to find the difference there because the models have been built to reproduce this scaling loss, essentially. So definitely what we need to do is go multimodal and multi-scale, and that's the point of foundation models here. Because as I said at the beginning, every different observatory gives us different physical information. And up to now, there's very little cross-talk about all these things. And now we are reaching at a point that, okay, we have Rubin here that look at optical stars and variability, as you have seen of black holes. But we have other observatories that are also taking big data in different wavelengths, and all of them, serving basically blindly the sky. And so how we correlate all these things, each of these is different information about the physical process happening at different scales and different regimes. And so that's the goal of the discussion we're having is, can we break this degeneracy somehow? And so I think AI could help in two aspects. It could help in improving the models, making more physical, instead of having here some kind of fine-tuned parameter, having some fundamental parameter that is shared across simulation, and helping accelerating this by linking scales. And if you have some physical model here that is really from fundamental principles, you can go and compare to the data. But instead of doing it in 2 dimensions, you can go and have a shared representative embedding of all this data at the same time. And hopefully there, by playing with these representations that you can now afford with foundation models, for example, you can maybe be able to do inference, but also constrain the models in a more physical informative way, right? So I stop here, and François will continue with how we do that.